Hello everybody, this is lesson 13 of the lecture International Economics. I will discuss slides 25 to 35 of chapter 2, Economic Growth in Open Economies. In this lesson I will review the Solow-Svern model for a closed economy, which we will open in the next lesson to analyze the interaction between international trade and growth. In chapter 2 of the lecture Macroeconomics, the neoclassical growth theory was discussed for the case of a closed economy, which means for the case of autarky. This was done to simplify the analysis. It implies that a country has no economic relations with foreign countries, so exports and imports are equal to zero. We know from our discussion of the balance of payment that domestic savings minus domestic investment must necessarily be always equal to exports minus imports. So if now exports is zero and imports is zero, the difference is also zero, so this implies that domestic savings must be equal to domestic gross investment. So in this case, savers can only invest their savings in the domestic economy. We will repeat this closed economy version of the neoclassical growth theory in the following, before we go on with the case of an open economy. A more detailed explanation is available in my macroeconomics lessons number 4 and 5. The Solow-Svern model is the textbook version of the neoclassical growth theory. The neoclassical growth theory has been empirically tested quite often and is well known for describing the data quite good. It is based on the idea that GDP production of a country can be described by a macroeconomic production function which contains all the production factors of a country. In this exposition of the macroeconomic production function, the y-axis measures GDP output represented by uppercase letter Y, and the x-axis measures the input of physical capital like production machines, buildings, infrastructure or vehicle fleets. The shortcut for physical capital is uppercase K. All other production factors are kept constant in this diagram. For example, uppercase letter A represents the stock of accumulated technological knowledge, uppercase letter B represents land and natural resources, uppercase letter P represents public goods supplied by the government like infrastructure or the legal system of a country. Uppercase letter L represents physical labor workers. Uppercase letter H represents the human capital of workers. This is their knowledge and their skills. And K is the variable we measure here on the x-axis, the capital stock of an economy. The stock of physical capital is a migration parameter in this diagram. This means if the stock of physical capital is changed, we migrate along the production curve along this line. The other input factors just mentioned are shift parameters. This means if their input quantities are increased, we have to shift the production function upward, and if their input quantities are reduced, we have to shift the production function downward. Now this green line represents the savings function of the economy. The Solow-Svern model assumes that every country has a constant savings ratio in percent of GDP, such that macroeconomic savings equal the savings ratio, here represented by lowercase letter s, times GDP. So if the savings ratio is a value below 100%, what is typically the case for Germany, s would be equal to 11%, the savings function lies always below the production function. For a hypothetical value of the savings ratio of 100%, the savings function would be equal to the domestic production function of GDP. Of course, this is not realistic, so typically we have savings ratio significantly below 100%. In a closed economy, domestic savings cannot flow to foreign countries, as already mentioned. Consequently, they must be invested inside the country, and as a result then domestic savings must equal domestic gross investment, for which we use uppercase letter I. So the savings curve represents in a closed economy also the gross investment curve. This green curve is the savings curve and at the same time the gross investment curve of this economy. Now to complete the Solow-Svern model, all we need is to add the depreciation curve. Under the assumptions of the Solow-Svern model, the depreciation curve is typically such a straight line. The slope of this line is determined by the depreciation rate lambda. Lambda tells us how much in percent of the capital stock is consumed every year or every production period in the process of GDP production. This special example for depreciation curve implies a quite high value for lambda. We can determine the value for lambda by calculating the slope, the value of the slope of this curve. For example, if the capital stock would be equal to the length of 7 little quads, 1, 2, 3, 4, 5, 6, 7, the depreciation curve tells us that total depreciation equals the length of 1, 2, 3, 4, 5 little quads. As a result, the savings ratio lambda equals 5/7, which yields a value of 71%. So this blue line implies a value for lambda equal to 71%, 0.71. A more realistic depreciation ratio for Germany, for example, would be somewhere between 2 and 3%. We use this very high value for depreciation rate here simply to make the graphical exposition somewhat easier. Now that we have completed the Solow-Svern model, we can start the analysis to what level this economy grows if we assume, for example, a historically given level of the capital stock like KT. This would be capital stock equal to 1, 2, 3, 4, 5 little quads. If we assume that the economy has reached this level of the capital stock, the resulting GDP will equal this level YT. Under the simplifying assumptions of the Solow-Svern model, this is equal with household disposable income. Since we have no foreign countries and we have no government, GDP equals disposable income. The savings curve tells us how much of this GDP is saved. So this line segment here would be equal to savings, and the remainder, this line segment here, is then equal to consumption. Since we know that savings is equal to gross investment, we know that if we subtract from total savings the depreciation of this capital stock, which is equal to this line segment here, we receive net investment. Net investment would then be equal to this line segment between the green and the blue line. Net investment equals the change of the capital stock. Therefore, we use the symbol delta K for net investment. We can now find the capital stock of the next period, T plus 1, by adding net investment to the capital stock of the current period. So all we have to do is adding this line segment here, net investment, to this capital stock we have currently reached. If we do this graphically, we have to add this net investment level to the old capital stock KT. So this net investment has to be added to this old capital stock KT. The length of this vertical bracket and this horizontal bracket is identical, as you can control with the help of a straight edge, for example. We can now determine the new GDP level of period T plus 1. This is our new capital stock. With this capital stock, we are now able to produce this GDP level, YT plus 1. If we subtract now again capital depreciation from gross investment, this is gross investment equal to savings. If we subtract capital depreciation, this line segment, we receive the new net investment level, delta KT plus 2. If we add this new net investment level to the capital stock KT plus 1, so this vertical bracket has to equal once again this horizontal bracket, then we find the capital stock in the period T plus 2. So this is then the new capital stock, T plus 2. With this capital stock we are able to produce this amount of GDP. And now this process repeats itself over a couple of periods. We find here again the new net investment level, we add this new net investment level to the old capital stock to receive the capital stock of the following period. You observe that net investment gets smaller and smaller the closer we come to this intersection point. In this intersection point, finally, net investment becomes zero and the capital stock does not grow any longer. The change of the capital stock from now on will hence be zero. So K star is the capital stock where capital stock growth and as a result also GDP growth ends. Net investment is zero in this point, and we call this state of the economy the steady state. In the steady state, the capital stock and GDP is stable. They neither shrink nor grow. So now we have developed the Solow-Swan model for the closed economy. In the next lesson we will open the Solow-Swan model for international trade and international capital flows, and then we will see how this affects this steady state level. So much for this lesson.